All right, guys, welcome back to our series of algebra revision. Now, in the last video, I ended up not finishing the last problem. I just faced technical difficulties and then also realized there was a mistake there. So I'll go through that again. So this will focus on indices, quadratic factorization, and completing with the squares. These are usually the things that they really like to ask as well for paper 2 as well as paper 4. All right. So without wasting time, let's get to indices. Now, indices or indices, as we would call it, has got, like I said, two types of questions. So you do have questions where they ask you to solve, and to solve when you're solving an index. Now, remember, please, an index is just a base with an exponent, right? That's so these are our indices. So the index is the exponent, and then the base is obviously the one that holds the exponent. Now, in this case, these were examples that I just drew from the syllabi. You may be asked, for instance, to say, okay, now I give you 32 to the power of x equals to 2. Let's solve the value of x. Now, how would you solve this if x is actually an exponent? Now, to solve this, you need to make the base the same. Make the base the same, which means this base here must be the same as the base on the other end. So to make the bases the same, you need to take the higher number so that you can actually make this base to be equals to 2 as well. But how do you do that? You need to take a look at how do I raise 32 to the power of 2 so that I can represent 32 to the power of 2 instead of just writing 32. Now, I always tell students as well, the best way to do any of these things is to always do your prime factorization. So 2 into 32 is 16, and then 2 into 16 is 8, 2 into 8 is 4, and 2 into 4 is literally 2, and 2 into 2 is 1, which means there is 1, 2, 3, 4, 5 twos. So which means I can now rewrite this as 2 to the power of 5, right? 2 to the power of 5 multiplied by x in this case. I don't want to put it in brackets because it's just going to waste time. And then this is just basically to the power of 1. Now, because the bases are the same, we can cancel the bases out. Once the bases are canceled out, we will now have a linear equation of 5 equals to 5x equals to 1. 5x equals to 1, which means now we can solve the value of x. And to solve the value of x in this case, we just need to divide both sides by 5, then which simply means x is equals to 1 over 5. Which means if I raise 32 to the power of 1 over 5, I'll get 2. Right. So this is just typical questions again that you can get. Sometimes it can become complicated, and you'll see the questions that we will review after this too. Okay, so again, I just said if you are given something that looks like this and they're asking you to find that, think of making the base the same. And if it's a non-calculated paper, then use prime factorization. Then you will just be able to do that. All right, so let's take a look at the second question. The second question, we've got 5x plus 1 equals to 25. X, and we need to solve the value of x. What value of x would make the left-hand side and the right-hand side to be the same? Now, clearly here, we've got a base of 5 and a base of 25. So we need to make the bases the same. To make the base the same here again now, I will take the 25, which is the bigger number. 2 doesn't go into 25. 3 doesn't go into 25. So 5 is it. 5 goes into 25, as we know, 5 times, and 5 into 5 once. So which means I can represent 5 as 5 to the power of what? 2. And then basically just x again. I could have done this and still have multiplied with x, but I'm just avoiding doing that just to make it short. All right. And then you have on the other side 5x plus 1. Now, because the bases are the same, what do we do again, guys? We cancel that, we cancel that. Then you're going to end up with a linear equation of x plus 1 equals to 2x. We want to solve the value of x. So typically, we can send the other x to the other side, or minus x on both sides, which will literally be that x is actually just going to be equals to 1. As you can see, x is literally just equals to 1. Right. So just like that. The key, remember, like I said before, make the base the same. If you're struggling to make the base the same, use your favorite friend, prime factorization. Right. With that said, let's take a look at the other types of indices that you also get. These are what you call fractional indices. Now, it's important to go through a certain key rules here. When you're dealing with fractional indices, you really need to understand your roots as well. So, but before I look at fractional indices from the roots angle, we need to look at the fractional index of just multiplying indices. So if I have a to the power of n and m outside, what do I do with the m? I need to multiply the m with the n. So my final answer will then therefore be a to the power of nm. But what if I have the following then? A to the power of n over m. This is a fractional index. Now, fractional index is literally just a root. So this here becomes the base of the root, and this will become the outside of the root. So if I was to simplify this, I would take the root of a, where I'll put m on the outside, and then n, like so. This is how we simplify this. Now, this basically stretches back to what we've done already with your square roots, your cube roots, a fifth root, whatever root. So if I was to rewrite this, it will basically be the square root of a, right? Now you would have noticed that 2 didn't go here because the square root is already just 2. And then 1 is just going to be like everything here to the power of 1, which won't make any changes. So if I have this, for instance, now a to the power of a third, then that will basically be the cube root of a power of 1. I'm using, again, what, guys? This rule. Equally as well, this would have been 5 to the power of the fifth root of that to the power of 1. Now, if there was any number here like 3, then this number here will become 3. If there was a number like 2 here, this number here will become 2. If, say, for instance, here there was a number 3, then this becomes 3. So generally, these are some of the rules you need to understand when dealing with fractional indices. Okay, so with that said, let's take a look at how we would then simplify these things in an exam scenario. So all of these problems that I will be doing for indices or indices, as we would call it, are all drawn from recent question papers, paper 4s, paper 2s. So the first one, as you could see, we need to use the first rule because it really does come in the form of a m to the power of this. So the first thing I need to do is do that. So I need to multiply this guy with everything inside me. So I do that. So literally, it's going to be x to the power of 2 times 3 over 2. I'm literally multiplying this with that. And I must also multiply it with a 4 at the bottom as well. So that also then becomes 3 to the power, 4 to the power of 3 over 2. I'm now not done up until the stage, so I need to simplify it. Clearly, the top one is the numerator is easy to simplify because I can just say 3 times 2 times 3 is 6 divided by 2 is basically 3. Or I just cancel out the 2's here, and I'm going to end up with x to the power of 3, which means the numerator becomes simplified. The problem comes in with this one. This is a fractional index. And I know that there's only one way for me to do this fractional index, like what we did before with the rules. If there's a 2 here, then I already know immediately it's going to be the square root. So if I was to rewrite this before I write it down here, it's going to be square root because it's a 2. Where does the 3 go? The 3 has to go outside like this. So that means rewriting this at the bottom becomes square root of 4, 3. But we all know what the square root of 4 is, actually 2. So we can simplify that. Square root of 4 is 2. That means 2 to the power of 3. And 2 to the power of 3 is literally just 8. So the final answer is just x to the power of 3, 8. Sometimes they will tell you just leave it in index form like that, or you can just go ahead and simplify. So your rules are ultimately the most important thing. Right. You would have seen that I said it does become complex at times. This was the problem I was doing in the previous video that I did not finish. So let's go through here now again. So immediately here, I know it's indices and they want me to either solve, but this time they not even ask us to solve. They actually wanted us to write m in terms of n, which means making m the subject of the formula of all of this. Now, clearly, the first things first, I need to just focus on the base because I can't do any solving here if the bases are not the same. So I know, okay, I've got 16. I just need to take a look at now what 2 goes prime factorize quickly there. Then I know that that's going to be the case. That means it's 4 2s and then 64. 16, 8, 1. How many 2s are there? 1, 2, 3, 4, 5, 6. Now, some people can do this mentally as well, which is still fine. You don't need to do this, but not everybody can do it. So I can rewrite this. So the first one, it's only 4 2s. So I'm just going to write 2 to the power of 4. Okay, then I'll just put the 5m outside. 4, I can also make the base the same. 4 is just basically 2 to the power of 2, which we could have also done the same way. And then this now becomes 2 to the power of 1, 2, 3, 4, 5, 6. We say it, 6 to n. Yes, this is division. So we want to make it linear. Division now, what do you do? Now, obviously, I can simplify this by just multiplying that by that. Then I will have 2 to the power of 20m over 2 to the power of 2 here equals to 2 here, which becomes 12n. So if I end up with something that's like this, now how do I simplify it? I mean, this is division. We know that with division, you're just supposed to, the base is the same. So we can just literally rewrite this with, you just always subtract the exponents. So this can just be written as 20m minus 2 equals to 2 to the power of 12n, which we can see here now. The base is the same, so we can just cancel that out. And as soon as you're done canceling that out, immediately you can now make it linear to solve it. So this is why I say now at times, yes, it can become slightly difficult, but not that difficult. Right, so then you end up with 20m minus 2 equals to 12n. They said we must write m in terms of n. Now, I did check the memorandum, but let's see what we can do here. For us to make m the subject of the formula here, we need to get rid of the 2, so we add 2 on both sides. They said let's find m in terms of n, and then we can just literally divide both sides by 20. And that's it. That's literally our final answer. Now, we could have also simplified this by dividing this also throughout just by 2 to make it simpler, but it wouldn't make any difference as per se. So I think this could be then our final answer. All right. So that's just again another example of solving indices. Then in exams, you can find this ones as well. These ones are by far the easiest. This is just actually simplifying. So this is just multiplication. 3 times 5 is literally 15. These are, this is multiplication. So you need to add the exponents. So t to the power of 15. This is a fractional index. But before it's a fractional index, we need to do it this particular way first because it's a to the power an to the power of mn here. So we need to multiply the m first. So we need to multiply this with that and this with that as well because there are two things here. There's 64 and there's also u. So then it's going to be 64, 5 over 6, u 36 multiplied again here now by 5 over 6. Now we need to again proceed to solve the following. And to do this, we can first rewrite this as square root of, no, sixth root of, because there's a 6 here. I'll write sixth root of 64. And then the 5, which is here, I'm going to put outside. And then for u, it's just basically directly multiplying now. And then simplifying, so that would be 36 multiplied by 5 divided by 6. So you've got your 36. So my pen was missing. So 36 multiplied by 5. And then you divide that by 6, which is at the bottom. All right. Then you get 30. So that's going to be 30. Now, this is not a problem that you'll get without a calculator. To compute this, you obviously just punch this section into the calculator. Then you get your answer, which will then also then end up with 30u. Right. So these are, again, typical questions that you can get on your paper 4. Right. The ones that are quite common on your paper 2 is your fractional indices that are just basically, it's a base with, you're just given a base with a power of a fraction. Either a positive power, a negative power, and you know if it's a negative power, you need to inverse it. All right, so this, they ask you write down the exact value, which means they want you to compute it on a calculator. So in this case, we already know it's a fifth. So we just have to go and rewrite this as square root, fifth root of 5, 1, and then you punch that into a calculator to get the exact value. Straightforward. This one here now, clearly, first things first, I need to multiply that with that, and I need to multiply this with that, which will then change everything. So it's going to be this to the power of negative 2 over 5. Is it negative 2 over 5? Yes. And then x here, 5 times negative 2 over 5. Now this is negative. Now we all know the rule for indices. When you're dealing with a negative, you first need to inverse it. So we need to inverse this guy. So we have to first write this as 1 over 32 to the power of 2 over 5. Then this one is just direct because it's just an exponent. So it will be 5 times negative 2, which will give us obviously negative 10. And then negative 10 will just give us negative 10 divided by 5. It will give us negative 2. So we end up with something that's like that, which also means that we can inverse this now because it also has got comes in the same form as that. So you know, we now have 132 2 over 5 times 1x2. Then yes, we can rewrite this, guys, as a root because now this becomes 1 over 32 fifth root of 32, and then you bring the 2 outside. You can compute that in a calculator times 1 over that. And then once you get your answer, you obviously multiply this guy here and that guy there and that guy there, and you will have your answer at the end. Don't have a calculator, that's why I'm just leaving it. I'm leaving it there. So, but do be aware for questions that are like this in paper 4. The ones that you'll find in paper 4 are the ones we can't compute. I mean, the ones that you can find with the in paper 4 are the ones we can't compute without a calculator. Paper 2, they will give you one that you can compute with a calculator because you you need to know certain roots already. All right. So this ones are equally also just fractional indices. So let's start. So here, find the value of this. They said find the value. Already you can see it's a fractional index, but it's a negative one. So it's going to be 127 over 3, right? Once inversed, I need to then rewrite this. So that would be 1 cube root of 27. You need to know what the cube root of 27 is, obviously. 2 cube root of 27 is just literally 9. I mean 3. So that will become 1, 3, 3 to the power of 2 is basically 1 over 9. So this you can find really on the non-calculator. Non-calculator. These are cube numbers, eh? That's why I'm saying cube root of 27. 3 times 3 times 3 gives you 27. Yeah, so it's cube numbers. You also need to know the same way as you know your square numbers. This is also a cube number. That's why you see here they put a 3 as well. So again, we need to rewrite this, but this we are not going to inverse because it's not to the power of a negative. So we can just directly write. That's going to be 125 cube root 2. Cube root of 125 is basically 5. 5 to the power of 2. There's a 2 here. And 5 to the power of 2 is basically 25. So these were some of the questions that actually appeared on the paper 2s. Quite straightforward. So you please acquaint yourself with your cube numbers. Cube numbers is just a number, a product of a number multiplied by itself. Eh? That's a cube multiplied by itself 3 times is a cube number. 1 times 1 times 1, 1. 2 times 2 times 2, 8. 3 times 3 times 3, 27. 4 times 4 times 4, 36. And then 5 times 5 times 5, 125. You know, those type of numbers. But don't go, just maybe go up until 7. Then they're never going to give you something greater than that. All right. Then again, this one, believe also came from a paper 2. So let's see. It's one that we need to inverse because it's to the power of a negative. So that's going to be 1 over 4 and 5 over 2 here. Then we know it's 2, so that's going to be square root. That's going to be square root of 4. Then the 5 we bring outside. Then we can write that as 1 over 2 to the power of 5. Then obviously, what is 2 times 2 times 2? That's already 8. Times another 2, that is 16. Times another 2, that is 32. So we can write that as 1 over 32. Sometimes they can ask you to just leave it here, or you can then have to do that. All right, another typical one where they will just ask you to probably express this into that. What this simply means is make this base here to be 2, right? And then you need to state y in terms of x. So let's try and do this. And it's just not, so we are not solving, we're just expressing. So here, what you need to do is, again, you just do your prime factorization, because you want to get that. And then you know it's 2 to the power of 3, so I can write that 2 to the power of 3, 2x plus 3. Then they said where this can literally be, um, this is actually what we are saying is your y. And that's it. That's it. Here they only said express. They did not say do any other thing. Just express. They didn't say solve. With that said, guys, that was the end of in indices. I think just practicing a few problems with this, you don't need to do 100. Don't kill yourself with that. Just at least do 5 problems of each. Um, and if you struggle, you can always go to your Cognito and then watch a video or so, but don't overdo it. It's not like you're going to get 10 questions of it. You will get 1 question of each, but it's 1 question of each that you're not supposed to miss. Then what we've done in class over and over again is quadratic factorization, and a very, very important skill. Like I said, it's also part of, stems from video number 1, but I said I was going to cover it only in video number 2. Now, factorizing or quadratic factorization, really, guys, we need to always find what we call our factor pairs. Be careful with this. And be very good with your factors also. So in this case, we are saying we've got a squared plus 15a plus 36. And we need to factorize this. We know it's a quadratic because it's in the form of ax squared plus bx plus c. So we have 1 times 36. And why am I saying 1? Because there's a 1 here, right? 1 times 36, so that will be 36. So what are we looking for? We are looking for factor pairs of 36. When we multiply them, we get 36. And when we add them, we're supposed to get 15. You know, what are those factor pairs? Clearly 31 times 1 will give us 36, but it won't give us 15 when we add it together. So then you need to start thinking. I mean, 6 times 6 is 36, isn't it? But 6 plus 6 won't give me 36. Can it? No. So what factor pairs can I use to actually then find this? So let's go. So we have the other factor pair. My brain is slightly slow today. Is it 9 times, 8 times 6, 6 times 6? Factor pairs of 36. Excuse me, guys, just struggling with my pen here. On this one. My apologies on that. Just bear with me, just fixing my pen, and I can't restart the recording again. Yeah. Okay. So where we? So we've got 36 times 6, like I said, and then we still have 36 times 1. What other things can give me here? I can literally just use 12 times 12 times 3. Okay, yeah, 12 times 3 is 36. So I could use this 12 times 6. If you struggle, then you can still use that other technique I taught you guys in class, where you try and look for your factor pairs using prime factorization. So 2 into that. 2 into this will give us 17. And then we don't have any other things, so this would not have worked as well. So just know your factor pairs. All right. 17 or 16, guys. 17. 18, actually, not 17. It could have worked. And then that will give you, what, 9? 3 goes into 9, and 3 into 3. Then you could have just try and see what numbers can you then use here to get yourself 15. Then you see here, if I use the 2 and 2 here, which is basically 4, and the 3, I'll get 12. So 12 plus 3 will give me 15. Oh, it could have worked actually. All right. So with that said, then you then start factorizing. So we can rewrite this as, it doesn't matter in which order, so I can just write 12a here plus, or maybe I can write the easier one here first, 3a, and then 12a plus 36. Then from there you go on with grouping. Now here the highest common factor here will be a, 3a plus, here will be 12. 12 goes into 36 3 times. Uncommon with uncommon. And then you end up with something that looks like that. I'm supposed to remove that a there. All right. So literally, guys, I was going rather way too fast on this one. Apologies. But I do assume that you guys know how to factorize. All right, so another example again, and you guys can do really more of your own, of your own practice on this. It's a very important skill. So here you'll see that the leading coefficient is not 1 as the other one, so you need to multiply the 2 here first. 2 times 1 is literally going to be 2. So 2 times 1 is going to be 2. Now we're going to look for factor pairs. Oh, I put an example that cannot be factorized because there's no way you can get factor pairs that of 2 which will add up to this, unless obviously if I just made this to be 2, then it can work. But nonetheless, forgive me for this again, quite fast, that it's actually out. But I do assume that you guys don't know how to do your quadratic factorization. Perhaps the one that I really should highlight is your completing the squares, which I know that people don't like memorizing that formula that I gave you, which is your x plus b over 2 squared minus b over 2 squared plus c. However, this is the only way in which you guys can really complete the squares. Now, in the exams, what they do is they will ask you to write it in a form that's like this. Immediately, they give you a quadratic expression. They say, this can be written in this form. Then they want you to complete the squares. They won't tell you directly that you must complete the squares. So what then should you do? You must identify your A and your B and your C. Your A is 2, your B is 12, and your C is -2. In completing of the squares, there is a rule. You cannot complete the squares if the leading coefficient here is not 1. So for this expression to work, we need to get rid of the 2. That means we need to divide every single number here by 2 so that the number in front becomes 1. So then we now are going to be left with x squared plus 12 plus 6x actually minus 1. Whenever you complete the squares, make sure that the leading coefficient here is always going to be 1. If not, then you must divide everything by the number that's in front here before you complete the squares. It's only for completing the squares. All right, now you end up with an expression that looks like that. What are we going to do with it? Our A now is actually no longer 2, it's actually 1, and our B is actually 12, and our C is actually -1. So then B is 6, and C is -1. We don't need A because we only need B. So we plug and play, substitute into that expression on top. We are going to have x plus 6 over 2. That's our b squared minus 6 again divided by 2. There's a square here again. Plus c. Our c is negative, so we just write negative. Then we simplify the brackets inside. So it's going to be x plus 3 here squared minus, literally here we're going to have again 3x squared minus 1, and end up with x plus 3 squared. And then here we will have -9, -1, which will literally end up with x plus 3 squared minus 10. So if you look at it in this way now, the value in front here is going to be 1. That's our A that they are asking for. The value of B here is actually 3. And the value of C here that they're asking for is actually C. So that's what they can ask you in an exam. So do know how to complete the squares. Maybe just one problem in paper 2 or 4. It doesn't really matter. All right. Then here, what do we have? Again, completing of the squares because they want us to write it in this format. This one, you can see it's good to go because the first variable in front is actually already equals to 1. So no need to divide anything as long as you know that to complete your squares, you need to apply that formula plus C. So I know already my B is -10, my C is literally 7. Right, that's going to be -10 here. I can still put the plus sign, but I know it's going to become a negative. -10 here, squared, plus C. Simplify. 2 into -10 becomes -5 squared minus, this is going to be 2 into -10 is -5. But remember now, this is in brackets. So -5 to the power of 2 is actually going to give us a positive number. And that is obviously positive 25 plus 7 then. So if you do that, you're going to end up with the following. And if you add 7 to -25, you end up with the following, -18. Which means now you see, when they say find the constants P and Q, where is your Q? Your Q is -18. Where is your P? Your P is -5. And you can see it's in that order. That's P and that's Q. So be careful when they say this, they give you a quadratic and they want it to be in that form, then they want you to complete the squares. Right, I was slightly rough on this video, but I just wanted to touch base on some of those essentials. And literally, I've just followed the syllabi. The next one, I'll be quite slow for Algebra 3 because that involves sequences. All right, we've come to the end of this video. I hope you guys are doing well and keep studying.